Okay, so a few messages. I guess the first message I want to convey, and I have seen your slide, a lot of you are working on photo dissociation region, photoionization region. You know that these are a huge subject in astronomy. So in fact, there are entire summer school which are dedicated to any one of these two aspects. So obviously, I'm not going to be exhaustive in 2 hours, and I had to make some very, very hard choice for this lecture. And the choice that I have made is to just present you a broad overview of the processes, and I should say the macrophysical processes that drive, that control the thermochemical state of photoionized and photodissociation regions, okay? And the underlying goal is that, in fact, the goal is that if at some point you are using some highly sophisticated model of photoionization and photodissociation region, then you know what this model are trying to do, what kind of physics they are trying to solve, and also you have some kind of idea of the complexity of the task. A second message that I've forgotten. What did I wanted to say? Yes, the second message is that I have tried, in fact, I don't know your level, I have tried to be as simple as possible. And in fact, I'm a little bit afraid that I will be too simple, that I will describe things that you already know. But if it is the case, then you can do something else. Well, you're not forced to listen to me. Okay, another important message are, of course, no, it doesn't work. Okay. What is happening? Okay. Okay, another message is, of course, the references. So all this lecture is based on several articles and several textbooks, but the basis or the foundation of everything I'm going to talk about are these 3 textbooks, the one by Osterbrock and Fairland, the one by Drain and by Dopita and Sutherland, and these 2 reviews by Hollenbach and Thielens in 1999 and by Wolfire in 2022. So the point I want to make here is that if you want to increase your knowledge in photoionization region and photodissociation region, I strongly recommend you to read all these references cover to cover. And if you do that, then I can tell you, you will know more than I do about photoionization and photodissociation region, because it's not entirely my field, to be honest. Okay. Next message, which is important, is about, of course, the code dedicated to the study of photoionized and photodissociation region, okay? So maybe you know that, but over the years, there have been several codes that have been developed by the international community dedicated to the study of photoionized and photodissociated gas. And a lot of efforts have been made by these different teams around the world to make their code public, to make their code available for download. You can download the code, run it yourself. In some cases, you also have access to pre-computed grids of model. So a lot of effort has been dedicated to that. And here, I just give you a kind of a list of the main code of photodissociation and photoionization region that are currently public. So there is the Cloudy model, the Mappings 5 code, the Meudon PDR code, the Cosmato model, and the UCL PDR code. So obviously, all these codes have their own specificities, their strengths and weaknesses, if you want. And for instance, you can see that some of the code are dedicated to photoionized gas, like for instance, the Mappings code, which can also do shocks, or the Cloudy model. And other codes are dedicated only to the study of photodissociation region, like this 3 code here. And some of them are more versatile, like the Cloudy model, which can do both photoionization region and PDR model, okay? The point I want to make here is that don't hesitate to download this code yourself, to run them, to download the results that you can find online, because I think this is the best way, in fact, to learn about the physics that govern this region. And one disclaimer, important disclaimer, in all this lecture, I will show figures, of course, and all these figures have been built using the Meudon PDR code and the Cloudy model. The reason for that is that I know a lot about the Meudon PDR code, and I know somehow a little bit about Cloudy models and the Mappings code, but I only know how to run the Cloudy model, okay? So if I made my figures with the Meudon PDR code and the clarity model, it's not because I believe that there are better codes. Huh? This is important, not to make an enemy out of the entire community. So really, it was done for personal convenience and by ignorance rather than by preference. Okay. So this being said, why do we care about photoionization and photodissociation region? So we care because in fact, this environment has a big chunk of astronomical studies. Huh? And it's very easy, in fact, to understand. Let's take, for instance, a galaxy. In a galaxy, you have several sources of high energy photons. So when I mean high energy photon, I mean photon capable of dissociating or photoionizing the gas. Huh? So let's look at these sources. First, you have stars, typically hot He stars or OB stars, or stars which are dying stars on their way to evolve towards the white dwarf phase. But in addition, in galaxies, you have active galactic nuclei. So in active galactic nuclei, you have the generation of high energy photon due to the accretion of matter onto the central object. You have also supernova and supernova remnants. So the idea there is that the kinetic energy of the blast is used to create a hot plasma that radiates in X-rays and in the UV also. And finally, at much larger scale, you have galaxy-galaxy collision, which basically does the same thing. You use the kinetic energy to generate a hot plasma that will radiate in X-ray, okay? The point is that if these sources of high energy photon were alone in the universe, then the astronomy will be simpler. I don't say that it will be simple, but it will be simpler in the sense that anytime you will point a telescope, you will see the direct source of emission of high energy photons, okay? But as you know, there is the interstellar medium all around. So all these photons generated by these events cannot travel freely. They interact with the gas and the dust, with the interstellar matter through scattering and absorption processes. And every time a photon is absorbed, it modifies the thermochemical structure of the gas and the dust, by the way, react by emitting a photon at another wavelength. So the outcome is that there is a reprocessing of all the energy that is absorbed by the interstellar matter. So when you point a telescope toward any astronomical sources, what you will see is the initial spectrum, which is modified through absorption and scattering processes. And you will see also the result of the reprocessing of energy. You will see the emission of the interstellar gas. And so if you want to understand observation, to connect the observation to your theoretical model, you need to understand this reprocessing of energy, and you need to understand the physics, the microphysical processes happening in photoionized gas and photodissociation region. So this statement is true at all scale, and this is why I put these four nice images here. It is true, for instance, if you are looking at planetary nebula, you will need to look at the interaction between the white dwarf at the center and the envelope, which is ejected. If you look at much larger scale at star-forming region, then you will need to do the same thing. Look at the interaction between a young star cluster with the surrounding interstellar medium. At much larger scale, if you look at the diffuse cloud and the first step of star formation, this is the same. And finally, if you look at the scale of an entire galaxy, then this is exactly the same problem. You need to understand all the interaction between these ionizing and photodissociating photons with the matter. And this is well represented with this image, which is a composite image. So in blue, you have the Chandra observation of the X-ray emission. In green, you have the starlight observed by Hubble, and in red, you have the emission by cold dust. Okay, so this is an example of the fact that if you look at this image, you need to understand the reprocessing of energy of the sources of high energy photons. So how are we going to do that? Just to have fun, let's look at the problem in its entire complexity, okay? So in its entire complexity, or if we are looking for complexity, we see that the first thing we could say is that all these objects are not 1D objects. And in fact, is very beautifully seen in images, for instance, of planetary nebula or H2 region, what do we see? We see cavities, we see bubbles, we see filaments, we see sheets, we see a lot of morphological structure. So the first instinct will be to say, okay, in order to study this region, we have to solve the propagation of photons in a three-dimensional environment, okay? The second thing that is not seen in this figure is that all this environment or all these objects are in dynamical evolution. So this is, so to illustrate this, I show you here the result of an animation that was done by Vincent Maillard for a very simple case. Let's say that I consider an ambient medium here, and suddenly there is a star that forms in this ambient medium. What will happen? So this is a problem, and the solution has been known, in fact, for many years. But basically, what the star will first do is that it will ionize the surrounding environment and create an ionization front that will propagate into the ambient medium. During the early phase of this evolution, the ionization front moves very fast so that the gas doesn't have the time to react to this new reality. So during this phase, which is called the R-type phase, there is no change in density between the ambient medium and the ionized gas here. And the effect of the star is not only to ionize this region, but to also heat the gas to very high temperature. So what the star will create here will be a pocket of very warm warm and ionized gas, okay? But at some point, which is called the when in fact the ionization front goes to the R critical velocity, what happens is that in fact this R critical velocity is basically close to the sound speed of the ionized gas. What happens is that the hot medium will want to expand into the cold medium, okay? And by doing so, it will generate a shock that will propagate into the ambient medium. And the goal of this shock will be to slow down the ionization front and also to increase the pressure of the ambient medium next to the ionization front, okay? So during this phase, which is called the D-type phase, the impact of the star will be to have created a pocket of low-density warm ionized gas and a shell of high-pressure neutral gas around it, and plus a forward shock that moves away from the ionization front. So this simple example is just to illustrate the fact that there is a dynamical evolution of this object. And if there is a dynamical evolution, then we can think that there might be some out of equilibrium effect on the thermal evolution and the chemistry. So in all its complexity, if we consider the entire complexity of photoionized and photodissociation regions, then we know what we need to do if we want to solve the problem, the time-dependent problem of 3D evolution of this region. Then first we have to solve the dynamics of the region. So we have to solve the so-called magneto-hydrodynamic equation, which are shown here. Then, since we want to solve the radiative transfer in 3 dimensions, we need to know the chemical composition of this region. So we have to follow the time-dependent evolution of the chemistry. For any species X, we need to follow the time-dependent evolution of the density of this species, taking into account the interaction of this species with the radiation field, but also the interaction of these species with one another. Since we want the absorption and emission properties of the environment, we also need to model the time-dependent evolution of the excited levels of all these species, okay? So for each species here, we need to model the evolution of the density of the excited level, taking into account, of course, all the interaction to form and depopulate this level. And finally, we need to solve the radiative transfer equation in 3D, in all directions and at every position, taking into account absorption and scattering processes and the emission by the matter, okay? And then, of course, we need to take into account all the couplings between these different parts. So obviously, and you probably all know that, this problem, the first remark that we can say at this point is that this problem is intractable. Even if you were to remove entirely the MHD and you only focus on solving the radiative transfer in 3D coupled with the chemistry, this will still be intractable. In fact, if you don't know that, I recommend you to read the book written by Chris Dulmont on radiative transfer in 3D, which is very nice and explain why radiative transfer by itself is complicated. So we need to make some simplification. The second remark that we can say is that, in fact, we don't need to solve all of this stuff, okay? In many cases, we can indeed make simplification. The first simplification is regarding the 3D structure. So typically, of course, when we are looking at photoionized and photodissociation region, they look 3D, but sometimes locally or over a sub-region, we can approximate this structure with 1D or 2D, let's say, morphology. Okay, so this is the first simplification that we can make. Second simplification is that indeed, all these environments are in dynamical evolution, but if the dynamical timescale is smaller than the chemical or thermal timescale, then we can consider thermochemical equilibrium, okay? And this greatly reduces the complexity of the task. So this is what I'm going to do, in fact, during this lecture. I'm going to make 3 basic assumptions, and this is not very original. Everybody is making the same when they do an introductory talk about this subject. I'm going to consider either spherical or plane parallel geometry. I'm going to consider that the gas is and the dust is completely static and at steady state, meaning that I'm going to consider thermochemical equilibrium. And the last assumption I'm going to make is that I'm not going to consider scattering processes. So while these 2 assumptions may be very valid in many environments, neglecting scattering is a bad idea in the photoionized and photodissociation region because scattered light, you see it everywhere in the universe, okay? If I do that, it's simply because I want to focus on one simple thing, is how the energy that is absorbed by the interstellar matter is reprocessed at other energy, okay? I want to focus on the reprocessing of energy and not on the scattered light. So within this simplification, in fact, every single photoionization and photodissociation region is completely driven by one simple equation, which is this one, the simplified equation of the radiative transfer, which basically describes over a path L how the light is absorbed and is emitted by matter. So what I will do during this lecture is just take this equation, apply it to several environments, and see how this equation is driving the thermochemical state of photoionized gas and photodissociation region. And as you can see here, in fact, on the left side, I will consider several environments. So first, I will talk about H2 region and planetary nebula, because for me, those stuff are the same. People will disagree with me, I guess, but I put them in the same category. Then I will focus on photodissociation region. And if I have time at the end, I will just make a quick overview about XDR, which are X-ray dominated region. So why do I make, or do we make, in fact, this subdivision here? The reason for this separation is due to 2 considerations. The first consideration is the impinging radiation field. What is the form and the intensity of the impinging radiation field? The second consideration is what is the main absorber of the region. So this is what I'm showing here and here. So on the top here, I show you just example of black body radiation for a temperature between 10 to the 4 and 10 to the 5 K, okay? And here is some kind of random radiation field, who cares? And on the bottom, what I show you here is the cross-section of absorption of different elements in any ionized state, okay? Scaled by their elemental abundance, okay? It's just to look at the main absorber depending on the wavelength. So imagine that I have an interstellar matter irradiated by this random radiation field here, okay? What will happen to the photon? According to this figure here, the first photon that will be absorbed will be basically photon between 13.6 and a few hundred eV, because this is where the cross-section are the largest. And it will be absorbed solely by 2 species, or elements, H and helium. And 3 species, in fact, H, helium, and helium plus. That's it. So this is what we define to me an H2 region. It's a region in space because in this region, while these photons are absorbed, you can consider that the photons on the other side of this region are not absorbed at all, okay? The length of absorption of these photons is too large compared to this one. So an H2 region will be a region where the flux of ionizing photon is large enough so that the gas is completely ionized, and where the thermochemical state of the gas is completely dominated by this photon, and the absorption is due to H and helium. Then, once all these photons are absorbed, what will happen? There is two cases. First case, let's say that there is no X-ray photon, or the X-ray flux is very small, okay? Then the physics of the gas will be completely dominated by this range of photon between 5 eV and 13.6 eV. Why 5 eV? We will talk what the limit, why is there a limit at 5 eV? We will talk about that later for photodissociation region, okay? And this radiation field will be mostly absorbed, according to this figure, by dust and PAHs. Don't know if I have to say dust or should I say cosmic nanoparticles? I can change my terminology. So, and this will be in typical cases, this will be absorbed by dust. So this will be the definition of a PDR. A PDR is a region where there is no ionizing photons and where all the physics is controlled by this range of photons. Now, the second case, imagine that the X-ray radiation field is not so low, okay? What will happen? Well, according to this figure, the photons are absorbed over much larger distances than the photon in PDR. That's true. But if the ratio of the flux in the X-ray domain compared to the flux of photon in the UV domain is large enough, even if these photons are absorbed over large distances, they have a very strong impact on the thermochemical state of the gas. And this is what will define to me an XDR. An XDR is a region where there is no photon in this range, okay, but there might be photon in this range, okay, where the photon in the X-ray domain have an impact on the thermochemical state of the gas. Okay. So this being said, we can start with H2 region. And in this part, I will consider this, in fact, configuration here. So I will consider either a shell of gas in a spherical geometry or a slab of gas and dust in a plane parallel geometry irradiated by one single source, okay? Since we want to have a photoionized region, I will consider sources that can in fact ionize hydrogen and helium. So typically the sources I will consider are either O or B stars or white dwarf, okay, if I want to model planetary nebula. And finally, what about the spectrum? To simplify things, I will consider that the shell of gas or the slab is irradiated by a black body radiation field. It's just to simplify things, but if we want, we can also use a more complicated radiation field, such as the radiation field that comes out of model of stellar atmosphere, such as those that you can download using the Pollux and the Phoenix database. So in this configuration, I will try to answer a few questions. First, what is the ionization state of the gas? What is the thermal state of the gas? And what is the typical emission of H2 region? And then I will try to look at a few examples. So first, what is the ionization state of the gas? Well, in H2 region, the ionization state is solely driven, in fact, by this simple radiative transfer equation, where kappa nu here stands for the absorption coefficient and G nu stands for the emission coefficient. So as I said before, in H2 region, the absorption is completely dominated by three species, H, helium, and helium plus. Now, what about the emission coefficient, this emission coefficient here? What we have to realize for H2 region, since we only care about propagation of photon between 13.6 and a few hundred eV, if the H2 region was not emitted by itself photon larger than 13.6 eV, then this equation would be incredibly simple to solve. We could remove, in fact, this term, and we could solve this equation step by step, starting from one border of the clad and integrating the opacity and calculating during this, or making the calculation at this time of the chemical composition of the gas that gives the opacity. The big problem of H2 region, and this is a major problem of H2 region, is that, in fact, it emits photon with energy larger than 13.6 eV, okay? The result is that there is some emission term in this range, and the result of this emission term is that there is necessarily in H2 region a non-local coupling. A photon that is emitted somewhere in the H2 region can be emitted in all the direction and ionize another particle at another position. Okay. So what are the emission processes? Well, basically, there are three processes by which you can emit photon larger than 13, with an energy larger than 13.6 eV. The first process is the recombination of an electron onto an ion. When an electron recombines onto an ion, it builds the ion, but with a lesser stage of ionization, and it builds the ion in one specific excited level, which is represented here by its quantum number, N and L, okay? And when there is this process happening, there is an emission of photons, which is highly peaked at the ionization potential of the level, but with energy slightly larger than the ionization potential. The second emission process is, of course, line process, so the de-excitation from one level to another, which can happen in the range of energy larger than 13.6 eV. So this is a typical emissivity with phi, the line profile. And the third process that can emit high energy photons is the two-photon de-excitation. So this two-photon emission process is due to the de-excitation of metastable level, which basically have the same emissivity as the one shown here, except that the photons are emitted over a very broad range of energy. So what we see here is that in H2 region, there are non-local coupling in the radiation field. And the second conclusion is that this non-local coupling is linked to the atomic structure or to the energetic structure of atom and ions. So to illustrate this, I show you here the three energetic structure of hydrogen, helium, and helium plus. So, and in violet, magenta, whatever, you have the ionization potential of hydrogen, helium, and helium plus. So to simplify, let's just look at hydrogen first. When we look at the energy structure of the hydrogen atom, what we see is that, of course, there is no line that can emit photon larger than 13.6 eV, evidently. In fact, in this case, there is only one process that can emit a photon capable of ionizing hydrogen. This is the recombination down to the ground state, because during the recombination, you will emit a photon with the ionization potential of hydrogen, plus, in fact, with an energy slightly larger, in fact, than this ionization potential. So if we consider only H, there is one source of coupling. Now, if we consider helium, then there is many sources of coupling. So for the same reason as for hydrogen, the only process that can generate a photon capable of ionizing helium is a recombination down to the ground state of helium, okay, which will generate a photon with an energy slightly larger than 24.6 eV. But there are several processes that can also generate photons that can ionize hydrogen. Let's say, for instance, that you have a recombination on one of these levels here. What will happen is that this level will cascade downward through line emission, and all these lines won't have the energy to ionize hydrogen. However, at the end, they will reach this 4 level, here, no, this 3 level, I should say, 1, 2, 3. And this 3 level will eventually emit a photon or a de-excite towards the ground state, and when they do, they will emit photons that can ionize hydrogen, okay? So the conclusion here is that there are sources of non-local coupling in H2 region, and these sources are linked to the energetic structure of the different atoms. And what we can already see here is that the nature of the coupling will depend on the radiation field that ionize your gas. So for instance, if you don't produce any photon capable of ionizing helium, okay, then you will have a strong coupling of hydrogen with itself, okay, but a small coupling between helium and the ionization of hydrogen. But as you start producing, or if you can produce photon with an energy sufficient to ionize helium, then you will have a strong coupling between helium and hydrogen. So now we can move and solve this ionization equilibrium. So basically, at every point in the H2 region, the ionization stage of, let's say, hydrogen, helium, and helium plus is given by this equation. So on this equation on the left, you have the photoionization rate, and on the right, you have the recombination rate of the species. So on the left, this ionization rate depends on G nu, which is the average intensities over all direction, which has two contributions, the intensity coming from the star and the intensity coming from the gas itself from the H2 region. And on the right, the recombination rate is simply the sum over all the level of the species of the recombination toward one level. So in practice, in H2 regions, since we have non-local coupling, this equation should be solved iteratively. First, to make an assumption regarding the radiation field generated by the nebula. Then you solve the ionization balance. Then you recompute the radiation field generated by the nebula, and so on and so forth, until you reach convergence. Okay. But in fact, there are several cases that are found in the literature, in the textbook, which are very useful. In fact, there are two cases of extreme limit for this problem, and those are called the case A and case B radiative transfer. So I don't know if you know that, so I will describe them. So to consider case A and case B, the more simple is to consider a pure H nebula. In the case A, what we basically assume is that the nebula is optically thin. If the nebula is optically thin, then it means that you can approximate the radiation field generated by the nebula and say that it is zero. And in this case, this equation is simplified to this equation where we only have a dependence on the radiation field emitted by the star. Okay. So this is a very simple equation that you can solve easily from one side of the nebula to the next, because there is no non-local coupling. In the case B, what we assume is that the nebula is optically thick 2 photons with an energy of 13.6 eV. In this case, what happens is that anytime there is a recombination of hydrogen down to the ground state, a photon is emitted that can ionize hydrogen. But since the nebula is optically thick, this photon will be reabsorbed by some other point in the H2 region. Okay. So what we can do in this case is simply locally assume, in fact, that this absorption happens at the same point of the emission. This is called the on-the-spot approximation. And in this case, what happens is that you can simplify on this equation the emissivity of the nebula locally with the recombination down to the ground state on the other side. It's as if recombination on the ground state don't happen at all in case B. And what you obtain if you do that is a very simplified equation. This is the same equation that is here, in fact, where this ionization balance only depends on the star or on the radiation field emitted by the star, but where you have simplified the recombination rate by removing the recombination toward the ground state. Okay. So basically, once you have this equation in a pure hydrogen nebula, you can integrate over 4 pi, then integrate over the distance. And what this equation gives you, and you can do it yourself, it's easy, it's the equation of the so-called Strömgren radius. Okay, so the Strömgren radius just gives you the size of the ionized bubble around the central object. Okay. So now we can move to the more realistic case, which is the ionization equilibrium when we take into account helium. So when we take into account helium, then we have to solve the ionization equilibrium for 2 species, H and helium, and these are the 2 equations that we obtain. So basically, these are the same equation as before. So you have the photoionization rate here and the recombination here, except that we added two terms. This term corresponds to the recombination of helium to the ground state, which can ionize hydrogen with a probability Y. And this term is a recombination of helium to any state, and some fraction of this recombination can lead to the ionization of hydrogen. Okay. Well, the point is that in typical case of H2 region, you can show that in fact P is equal to 1 in this equation, meaning that every time that you have a recombination of helium in any level but the ground state, it will lead to one ionization of hydrogen. And if the blackbody temperature is small, then you can show very easily, in fact, that Y is equal to 0, meaning that every time you have a recombination of helium plus in the ground state, it will ionize helium and not hydrogen. So if you make this simplification, then in this equation, you obtain this very simple equation here, which basically what we see here is that those are two equations that are independent for helium and hydrogen. So the outcome of this study here is that you have two equations that describe two Strömgren bubbles, one for helium and the other one for hydrogen. Okay. And this is what we obtain, in fact, in numerical simulation, in actual models. So this is a figure that has been obtained by Claudi. And the idea is that, and in this figure, I show you the ionization stage of, or ionization fraction of hydrogen here and helium here as a function of the blackbody temperature of the central source. Okay. So what you can see is that at small blackbody temperature, we indeed have two Strömgren spheres, one for helium here and one for hydrogen, which are decorrelated from one another. And then when you increase, in fact, the blackbody temperature, what you will have is that the helium plus Strömgren sphere will increase in size until it reaches the hydrogen Strömgren sphere. And an even larger temperature, what is predicted is that, so this corresponds to temperature of planetary nebula, in fact. This corresponds, then what you will have is the formation of a helium plus core, and that's it, okay? So this is, in fact, almost the entire complexity of the ionization structure of H2 region. Once you have computed the ionization of hydrogen and helium, then all the rest follows, okay? You just need to solve this equation for hydrogen and helium, and then the rest of the structure is a consequence of it. So to illustrate this, I show you, in fact, here, the ionization equation for any elements heavier than hydrogen and helium. So for this element, in fact, this equation is basically the same than the one that I showed before. You have the photoionization rate here, and you have the radiative recombination rate here. But for heavy elements, this equation appears to be a little bit more complicated because you have to take into account additional terms. So for instance, you can take into account collisional ionization. And on the other side, you need to take into account the electronic recombination and charge exchange. So this equation seems more complicated, but in fact, it's much more easy to solve than the previous equation because you know the radiation field. You have computed the radiation field, which came from the transfer and the ionization balance of hydrogen and helium. So this is what is shown in this table. Once you know the ionization balance of hydrogen and helium, all the rest is determined. And in fact, what this table is showing is the main ionization stage of different heavy elements, depending on the zone you are looking at in the H2 region. And this is what I'm showing also in this last figure here, which basically shows the ionization fraction of oxygen for different blackbody temperature. And what we see is that at small blackbody temperature, we only have O+, in fact. And as the blackbody temperature increases, then we start to form O in different ionization stage. One fun result here is that the transition O+ to O, okay, if you look at these different figures, the transition O+ to O is always locked in H2 region to the transition H+ to H. And the reason for that is because of charge exchange between O+ and H at the transition between from H plus dominated region to a H dominated region. Okay, so now that this is done, we can move on and try to look at the thermal state of H2 region. So in fact, the thermal state of H2 region is a very beautiful result of microphysical processes happening in photoionized gas. And it results from of course, the heating and cooling mechanism of the region. So in H2 region, the main heating mechanism is the photoionization itself. And it simply writes like this. So with this simple equation, basically the total photoionization heating rate is just the sum over all the absorber of the rate of absorption of photon. And each time we absorb a photon, this photon leads to the production of a photoelectron, and this photoelectron at this energy, nu, or the h nu, sorry, where nu is the frequency of the photon, minus the energy of ionization of the species. And this is the heating mechanism. Photoionization generates electrons that then thermalize with the ambient gas. So in this equation, of course, G nu is a sum of the radiation field coming from the star and the radiation field coming from the nebula itself. So when we look at this equation, the first instinct that we will have is to believe that the heating rate due to photoionization is directly proportional to this intensity of the radiation field. But in fact, and this is a fun fact about H2 region, it's absolutely not the case. And the reason is because we have this factor here. When we increase the radiation field of the source, what happens is that we destroy the species, we ionize the region, and so we decrease, in fact, so what happens is that the density of the species decreases at the same time, and it's roughly inversely proportional to the intensity of the radiation field. So in fact, to illustrate this, if we look at a pure hydrogen nebula and we plug the ionization equation that we derived before, then we can get this equation for the total photoionization heating rate in a pure hydrogen nebula. And what this equation is showing, so the 3/2 of KTI is in fact the mean energy of a photoelectron for each photoionization. So what this equation shows is that in fact the heating in H2 region doesn't depend on the strength of the radiation field of your star, for instance. But it only depends on the shape of the radiation field through the mean energy of the photoelectron produced. The second thing that you can see is that this equation shows that the photoelectric heating appears to depend on the kinetic temperature of the gas, which was not obvious, in fact, from this equation. So when we look at this term, we finally obtain this figure. So here I show you the heating rate due to photoionization as a function of the kinetic temperature. And we see that there is indeed a dependence of the heating rate on the temperature, but only a weak dependence on the radiation field emitted by the central star. If I modify the effective temperature of the central star, so when I do that, I modify by a factor of 10 the flux emitted by the central star, and it only modifies by a factor of 2 the heating rate, and this is due to the change in the mean energy of the photoelectron. So now we can look at cooling mechanism, and basically in H2 region there are 3 main cooling mechanisms. The dominant one is cooling by collisional excitation. So you know this cooling. So to compute this cooling, we need simply to do the sum over all the species and all the collider and all couple of level of excitation and de-excitation processes, and take into account the fact that each excitation will lead to a loss of energy for the gas, and each de-excitation will correspond to the heating rate. Now, the second cooling, or source of cooling in H2 region are the recombination. So when there is an electron recombining onto an ion, basically the electron will lose its kinetic energy. So in order to compute the cooling rate associated to this process, we just need to do the sum over all recombination processes of the rate of recombination. So this is what you have here. And for each recombination, we assume that we lose 1/2 of mv squared for the electron energy, but we have to integrate this over the distribution of velocity of the electrons that we assume to be Maxwellian, which in fact is Maxwellian in an H2 region. And finally, the last process which accounts for the cooling is the free-free emission. So the free-free emission is when you have an electron traveling in an ionized medium, then the electron is accelerated by the charges around, and an electron which is accelerated radiates away. So this is how write this cooling term. This is simply a sum over all interaction between electron and the ions of the medium that generate an emission of, in fact, of photon. So in the end, when we sum all these cooling terms, we obtain this very famous cooling curve of H2 region. So obviously, this cooling curve is not universal. Huh? When you look at H2 region, depending on the position you are, it will depend on the chemical state of the gas at a given position. So for a different position, you will obtain a different cooling curve, okay? But generally, the cooling curve always looks something like that, in fact. And the reason is very simple, is that at very small kinetic temperature, the gas can only excite low-lying energy level. But as the temperature increases, at some point, it will start to excite electronic levels. And this always happens at this, roughly the same kinetic temperature. So the outcome is that when you look at the cooling curve of H2 region is completely dominated by fine structure line for this range of temperature. Then when we reach 10 to the 4K, this cooling curve is dominated by the so-called metastable lines. You start to excite metastable levels of different species, most notably O2, O3, and N2. At larger energy, the cooling is dominated by electronic resonant lines. So you excite more and more electronic level, which de-excite towards the ground state in resonant lines. Finally, at very large temperature, the cooling is dominated by the free-free emission. Okay. Okay. So now that we have this, we have all the ingredients to compute the thermal state of H2 region. And all we have to do that is to equal the heating rate to the cooling rate at equilibrium. And if we do that, here's what we obtain. And this is a major result of H2 region. Basically, H2 region have very well-defined kinetic temperature, which is always around 10 to the 4K. And the reason for that, there are two reasons. The first reason is that there is a sharp increase of the cooling rate at 10 to the 4K due to the excitation of metastable levels. You see that when you increase the temperature by a factor of 2 in this range, you increase the cooling rate by a factor of 10 to the 3, okay? And at the same time, as I shown before, there is a weak dependence of the heating rate on, let's say, both the temperature and the blackbody radiation field, okay? And this weak dependence means that you will always obtain the same kind of equilibrium for the thermal state of the gas, and it will always be around 10,000 K. So depending on the model parameter, you can obtain temperature between 7,000 and 20,000, but this is a very limited range. Huh? Okay. So now that we know the ionization stage or ionization state of the gas and the thermal state of the gas, we can compute the emission of H2 region, typical emission of H2 region. And this is what we obtain. So on this figure, I show you an example of a spectrum obtained with cloudy in a planetary nebula, I think. So it was with, in a gas with a density, an electron density of 10 to the 3 per cubic centimeter, irradiated by a black body at 10 to the 5K. Okay, so in black, you have the luminosity of the impinging spectrum, and in red, you have the result given by Claudy, which is the spectrum, the output spectrum emitted by the planetary nebula. So what this figure shows basically is a reprocessing of energy of all the photons of the source here, which has been absorbed and re-emitted at other wavelengths by the interstellar matter. So the second thing that we can see in this figure is that we basically see in this spectrum all the features that we have talked about before. So except for dust emission, but I'm going to talk about that later. So basically what you see in this spectrum typically is the two-photon continuum emission, which appears a bump here. We see the recombination continuum emission, which appear as sharp edges at these different wavelengths. We see in the optical range a series of forbidden, resonant, and recombination lines. We also see them, in fact, all these type of lines in the near infrared. And if we move to the near infrared and far infrared part of the spectra, what you will see is a combination of recombination lines and fine structure lines. So the last question that I would like to address in this part is how we can use the prediction of the model to constrain, in fact, observation, or to interpret observation to get the physical condition of H2 region out of observed spectra. So obviously, yes, something that I've forgotten to say, but obviously I'm not going to describe, in fact, all these features. And what I also want to give you is an idea, in fact, of the main emission lines or processes that you can have in different wavelengths. So this table is a summary of the main emitter at different wavelengths and was taken, in fact, from drain. So in fact, if you look at the optical part of the spectrum, your spectrum, typical spectrum of an H2 region, will be completely dominated by two kinds of lines, the recombination lines and the forbidden lines, okay? So regarding recombination lines, in H2 region, you will always have recombination lines of hydrogen, okay? But as we have seen before with ionization structure, depending on the black body effective temperature that you apply to your H2 region, you may see or not E1 recombination line, so recombination line of helium. Now, regarding the forbidden lines, these are the typical forbidden lines that you will see in any H2 region. So you will see lines from N2, O2, O3, S2, and S3. And among all these lines, the most powerful of all is these O3 lines have 5,000 angstrom. And in fact, this is why if you look at an H2 region with your bare eye, what you should see, in fact, is a greenish environment. And the reason for that is that the main emitter is O3, which emit in the green part of the spectrum. Now, if we go at larger wavelengths, what will dominate the spectrum is basically the fine structural one, and especially the fine structure line of O3, neon 2, and S3. So, okay, maybe I don't have time. So in fact, all these lines, and of course, all other lines that can be emitted in H2 region can be used, in fact, to extract some useful information about the physical condition of the gas. So I'm not going to present that because I've talked already for almost an hour. But basically, you can get out of the observation many information about the H2 region, like, for instance, the electron temperature. But you can get also the electron density of your H2 region using, in fact, the combination of several lines of the same species. We can talk about that later if you like. Huh? And you can also have some diagnostic about the central source, and this is called the Zanstra method, so I will also skip that. And as a conclusion to this first part, I would like to show you one example of application of the theory of H2 region, which is the Orion Nebula. Okay. So the Orion Nebula, so it's not a random example. The Orion Nebula is simply the brightest H2 region in the sky. And the reason for that is not that it is particularly luminous, it's just that it is the closest H2 region from us. It's located at 500 parsec from the Earth. So to make a long story short, this is a Hubble image of the Orion Nebula. And if we zoom at the center, we see what powers the nebula. In fact, this Orion Nebula is powered by a young cluster and most predominantly 4 stars, which are called the trapezium cluster and which are here. So these stars have created over the years a bubble of ionized gas. So this is the photoionized region or the H2 region of the Orion Nebula, which appear in yellow in this picture. And why in yellow is simply because it's a combination of H-alpha emission, S3 emission, and O3 emission. Okay. We see that this H2 region is bounded at the southeast by some structure, which is in fact a photodissociation region. So this is why the Orion Nebula is a very nice test case study of photoionized and photodissociated gas, is because it's a bright H2 region, and next to it, you can also study photodissociation region. So there have been many images taken from of the Orion Nebula. So I will just show 2 images, additional images of this region. So this is a very nice picture that was done by Javier Goicoechea in 2017, which basically show a combination of VLT observation and ALMA observation. And what you see in this picture is in green, the ionized gas, and in red, typically, the molecular gas associated to the Orion bar. And most recently, we had a very nice picture obtained with the JWST, which basically shows the emission of pHs and H2 in the Orion bar here. So what did we extract out of all this, the observation of the Orion Nebula? Basically, these are the main characteristics of the Orion H2 region. So typically from radio free emission measure, you can get the size of the H2 region, which is about 0.5 parsec, but you can also have an estimation of the electron density, which is about 3×10⁻³ particles per cubic centimeter. From the H recombination line, you can get the temperature of the electron, kinetic temperature of the electron, which is about 8×10⁻³ Kelvin, which is roughly what we expect for H2 region. But you can also get an estimation of the total flux or the total number of ionization of hydrogen that you can compare with what you would expect, the number of ionization you will expect from the star cluster and the trapezium cluster. And in fact, you see that these 2 estimations roughly agree with one another. And finally, from all the observations that has been performed, for instance, with the VLT, you get a lot of couples, combination, in fact, of lines, forbidden, resonant lines, and so on, that you can use to derive the electron temperature and the density of the gas. And here are the results that have been obtained, for instance, by Esteban in 2004, which shows that the typical kinetic temperature of this Orion Nebula, H2 region, sorry, is about between 8,000 and 10,000 K, which is roughly in agreement with this value here, and with an electron density which varies a lot, in fact, between 6,000 and 10,000. But this is to be expected because, in fact, when you look at images of this H2 region, you see a lot of morphological substructure, in fact, filaments and so on. And these are these filaments that you analyze, in fact, by Thanks. So yes, what I was saying is that you obtain, in fact, from these lines, several estimations of the density of the electron, which are different from the mid-density, and this is not very surprising. When you are looking at the Orion H2 region, what you see is a lot of substructures, and it's normal that the analysis that you are doing on line emission is biased toward, in fact, this substructure with high densities. So I think I'm going to stop here because I have, I mean, at least for the first part, for the H2 region part. As you have seen, I have tried to. Yes. So I have tried to just give you a kind of broad view of the main microphysical processes at play in H2 region, but there is a lot of things that I didn't talk about. I didn't talk about grain interaction, for instance. Grain are important in H2 region because they absorb the light, but so they also interact with all the atoms and all the ions. I didn't talk about a very nice effect of H2 region, which is the thermalization of high energy levels of atoms, which can be very important for the interpretation of observation. And I didn't talk at all also about radiative transfer algorithm and so on. So there are many subjects I didn't even touch for H2 region, but we can talk about it after this lecture if you like, okay? And finally, I didn't talk about the model. So this is why what this slide is for is just to give you an idea of the complexity of the most sophisticated model that currently exists regarding H2 region. So these models are sophisticated not only because of the input radiation that they can use, but also about the geometry that they can treat. And sometimes the model can treat time evolution, in fact, of H2 region. And they are very powerful also because all the microphysical processes that they include and they treat, which I didn't present in length in this part. So I can stop here for a few minutes if there is a question. No, this was the plan. Okay. Ouais.
Okay. So you speak about bubbles, and at some point you said that the interstellar medium is clumpy or filamentary or whatever. And so which kind of geometry do we keep geometry that is like bubble-like, or do we have a geometry that evolves quite a lot because of the stuff that you encounter in the medium when the H2 regions increase?
In reality, you want me to have? I have no idea. I mean, okay. If we are talking only about wait, I look ridiculous. If we are talking only about H2 region, what I have described for the evolution of H2 region neglects a lot of things, like the winds of the star, and like the kind of thermal instabilities that you, or whatever thermodynamical instability that you can have in this kind of object. So I'm not sure you want to know if what is the evolution of this filamentary structure within an H2 region, right? This was the point, huh? Okay. This, honestly, I don't know. I will guess that they are maybe bound to disappear. I don't know. Honestly, I don't know. What is the evolution, temporal evolution of this clumpiness? I don't know.
Was some more questions? Don't spare me, it's better.
I have a very basic question about this. When we're talking about the first slide about the Stromgren radius, So the first thing is it's not like at some point of time the ionization is not going to be zero. It's will be like a very vague boundary between that. So do we consider about 90% of ionization when like at some point of time 90% of the gas is ionized and that is considered to be as a Strongman radius, or the fraction is something else?
I guess I didn't get the entire question. How do you?
Sorry.
No, your question is when do we
What-
consider
what
that
is
the
the
Schramm-Kohn radius is
Yes.
there? Yeah.
What is the real limit for this?
What is the real limit?
Like what we consider while we are doing in literature and mostly.
In the literature, I don't know what is considered as a real limit. I just know from the theory what you will get as a limit. In fact, you can put the limit that you want. It's that usually the limit is done when the density of H plus is equal to the density of H in a steady state static case. Okay.
Yeah, in kind of when the density of H, let's say oxygen 3 ions, so oxygen 3 decreases about 90% or something. No.
Well, the Schramm-Kohn radius in theory is you can do whatever. But are you talking about? Are you talking about observations?
Yes.
You are talking about observation. How do you define the Schramm-Kohn? Okay, this honestly, I don't know. It's not my. I don't know. It's not my field.
Okay.
No, but it's true. I never did. I'm sorry. In fact, I did give a lesson. I never did any work on H2 region. I want to be clear on that. I never did any work on H2 region or photoionized gas. So everything I know, you know.
And the second question, okay, I was going to say, I can try and answer this. Sure, please. I have one more question. Okay, sure.
So, yeah, observationally, it's hard, right? Because the ISM is not, it's diffuse, it breaks up. Even you can see that even in Orion, where we get that resolution, you can see that some parts are quite sharp. So theoretically, the Strongman sphere works, right? So if you look at the Orion bar, there you go ionized gas, pop, molecular gas. Okay, and that's what the Strongman radius stands for. But then you look in other directions and it just seems to peter out. So observationally defining an edge is hard. Theoretically, when you'll see in most ones that it just cuts out. And so observationally, what we try and do is define when this, the H alpha quite generally, which is generally the strongest line for most H2 regions, transitions from very bright to diffuse is what we define the edge of a H2 region observationally. Exactly where that boundary is still debated. It's a hand wavy thing. So you look for something where the transition of H alpha is sharp and you say that's your Strongman radius. And so that's our best estimate. Many people use other definitions in terms of surface brightness, things like this. Okay, but like you can hear, this is a ongoing problem of where do you define the edge of a H2 region? Okay, and it gets even harder as you move further away. So outside the Milky Way, Magellan clouds, we can again try and define this. And again, we're looking for sharp transitions in the H alpha emission. As we move to nearby galaxies, it gets harder and harder because resolution smooths everything out.
Was your second question very short?
Oh yeah.
Okay.
Probably. Okay, I can. Fine. So the second question is about let's suppose of two H2 regions. One is singly like ionized by single star, and one is like multi-star systems in there. So how does the dynamics change there? Because in the multi-star system, there will be a lot of O and B stars, like clusters in there. So it will be, winds will be high, the outflows, like not outflows, kind of shocks will be there. And
well, yeah, but you describe it, I think you describe it the best way we can, in the sense that when you put for me, with one star, you can have wind, you can have shocks, you can have X-ray emission. This is what you see, in fact, in some observation of this region, I think. And when you put, in fact, multiple star system, what you have is basically a demultiplication of all of this, all these events, I would say. But maybe Brent will have a different answer to to this.
I was wondering about using H2 regions or H alpha as a proxy for star formation. Like what kind of observationally, what is the delay between the onset of star formation and when we're able to observe an H2 region? So yeah, are we like
what is the delay between, this is a good question, it's fun. What is the delay between you start to form a star and then when you can observe the H alpha emission? I don't know. I guess, well, right at the beginning, when you form a star, you have an immediate ionization region that forms. And the dynamical evolution, the time-dependent evolution is that you ionize almost instantly your immediate environment, and then the ionization front propagate very fast. I think that the typical time scale to reach the Strömgren radius, for instance, is of the order of, in typical H2 region, is of the order of 1,000 years or something like that. Huh? So it's very quick. Then, do you have to wait? For me, what I was trying to think is, do you have to wait until you have the Strömgren radius entirely to see something? I guess not. Of course, you will see at this point, you will see the maximums that you can see, okay? But I guess you don't need to wait for this point, right?
Oh, Melanie says that she will discuss that next week.
Ah, okay, cool. Well, she
Yes,
said that
maybe
a long time ago, or just okay.
Okay, so next question.
Thank you. I was wondering, you mentioned that when you calculate the O3 structure, the ionization structure in this H2 region, you said that this whole structure is determined by the H and helium, the hydrogen and helium.
No, H plus and H transition.
Yes, but I'm thinking like for oxygen, you must have some diffused radiation field, that like the contribution from that oxygen, because
from oxygen to the ionization.
Yeah, other or as well as other elements, nitrogen or something. Why do you consider those two? Is that the most abundant?
Exactly. In fact, it is exactly for the same reason as, you know, when you look at absorption of photons, you only consider this because those are the dominant elements. Okay.
Right.
So, well, in fact, I should go back to this figure. You see that the absorption cross section is much larger for when you scale it with the elemental abundance. This is important. It's much larger than for heavy elements. Okay. So now let's go back to this page or this slide. For the absorption, we are dominated by this species. What about the emission of photoionized, the emission of photoionizing photons, right? This is what you are asking.
Yes.
It's based on these three equations. But look, in these three equations, what we have is the density of the species that will recombine, for instance, and the cross-section of ionization. So for the same reason that absorption of photon is dominated by this species, emission of ionizing photon is also dominated by this species. You don't need to, you could, in fact, in models, I think that they consider everything, in fact. Everything is coupled because they want to treat with as much detail as they can the microphysical processes happening in an environment. But in the first approximation, it's not bad to consider that the only photons that can ionize the gas are emitted by these three species here.
Right. So if I run a cloudy model, so all these should be treated like coupling together in a self-consistent way. Right?
If what?
If I run a cloudy model.
Yeah, if you run a cloudy model, well, this is a good question. This is a good question that you should ask to Gary Ferland. And no, honestly, because I would want to say yes, because those models, it's always incredible when you look at what they are doing. Oh, I know what you can do. You can ask what they do in mappings. You do that, right? You take it. Does it change things? Okay. Thank you.
So I think we should maybe move on.
Yes.
Because I don't know how long the second part is.
It's longer than the first one.
Oh.
But
I had you to help us here.
the point is that the first one, I was not very comfortable giving that. Maybe I won't be comfortable giving the second one, but at least I know a little bit more about photo dissociation regions.
So yeah, maybe then let's move on.
Okay, let's move on. Very well.
And if there are leftover questions, of course, they can go into the lunch and coffee breaks.
So in this second part, I'm going to talk about photo dissociation region, which I know a little bit more. And in this part, I will forget about the spherical geometry and will only consider a plane parallel slab of gas illuminated from the left by some radiation field. The assumption, or not the assumption, but the definition of the PDR is that all the photons with an energy larger than 13.6 eV have been entirely absorbed. So we only need for a PDR to consider, in fact, the evolution or the absorption of photon between 5 and 13.6 eV. Why is there a limit at 5 eV? The reason is very simple. In fact, there are two reasons. First, photons with an energy below 5 electron volts are not energetic enough to photodissociate molecules. This is not entirely true. There are some molecules that can be photodissociated with lower energy photon, but those are trace molecules which won't change the chemical structure of the gas. Second reason is that photons with energy smaller than 5 eV are not energetic enough to induce a photoelectric effect, okay? So photons below this energy won't have any impact on the thermal structure of the gas. Now that this is said, what is the radiation field that we are going to adopt, to put on the left side of this cloud? Well, we could do the same as for H2 region and take a black body radiation, but this is not what is done by the PDR community. Usually the PDR community has a convention used for reference the so-called standard interstellar radiation field that you can see on this figure as a function of the wavelength. So what is the standard interstellar radiation field? It's the radiation field that you would see if you were not far away from the sun, but still in the solar neighborhood. This is the mean radiation field emitted by the star and the matter around you when you are in the solar neighborhood. So basically, what I will do here is the same. I will assume that this cloud here is irradiated by the so-called Matisse radiation field, which corresponds to the green point in this region. And I will assume that this cloud, I can play with this radiation field with a scaling factor called G0, okay? This is a typical way of modeling a PDR. So now, yes, let's have just first an overview of the kind of thermochemical structures that you would expect in this configuration. And we will start with this first point here. So at this point, obviously, all the molecules are destroyed, okay, by the radiation field, or most of the molecules are destroyed. So the gas is mostly atomic. And since we don't have any photon with energy larger than 13.6 eV, the chemical composition of the gas is basically given by this figure, which shows the ionization potential of different species as a function of the atomic number. So all species with an ionization potential larger than that of hydrogen are mostly neutral. This is the case of helium, nitrogen, oxygen, and so on. And all the species with an ionization potential smaller than that of hydrogen are singly ionized, so typically carbon, magnesium, silicium, and sulfur. So there are 2 points to take from here. The first point is that a PDR will be mostly a neutral environment with only some traces of ionization, okay? And the second point is that oppositely to H2 region, we don't have to consider multiply ionized species or doubly ionized species, okay? They are not present in a PDR environment. So now starting from this point, here is the typical thermochemical structure that you would expect to have in photodissociation region. So this is a complicated figure, so I'm not going to describe everything, but basically it gives you the thermal evolution and the chemical evolution of the gas as a function of this variable, which is the visual extension. So be careful. In PDR, we often, when we want to show profiles or spatial profiles of the photodissociation region, we often use this variable as a natural variable to display this profile. This is a visual extension, and it basically corresponds to the number of mean free pass of a photon at visible wavelength. So when you have an AV of 10, it's a distance expressed is the number of, let's say, mean free pass of a visible photon. Okay, so what we can see in this diagram here is that what we expect for the thermal evolution of the gas is that at the border of the PDR, the gas will be more or less warm between 100 and a few thousand K. And as the radiation field is absorbed, the gas becomes colder and colder between 10 and 100 K. And on top of this thermal structure of the PDR seems to show some chemical transition. So first, at some point, we see that there is a transition from atomic to molecular hydrogen, okay? But at another point, we see that there is some kind of transition, which is called the C plus C CO transition, where we switch from a medium where most of the carbon is in C plus to a medium where most of the carbon is in CO. This, in fact, combination of thermal structure and series of chemical transition is what makes PDR very interesting to study, because the fact that there are several chemical transitions on top of a thermal evolution will mean that the PDR will activate in each of these zones a different kind of chemistry, and this chemistry will lead to the production of a myriad of molecules that will not only trace the physical condition at this point, but that also will encode the entire global physical condition of your PDR, okay? Okay. So the question is, what drive this thermochemical evolution? And to look at this, we have to come back to this radiative transfer equation and look at absorption and emission coefficient. So basically, as I said at the beginning, the absorption of photon in a PDR is mostly dominated by dust and PHs. In fact, dust and PHs absorb more than 95% of all the photons in the range between 5 and 13.6 eV. Now, what about the emission coefficient? Well, if we look at all the photons that are absorbed by dust, then only a fraction of these photons will lead to a photoelectric effect, so will transfer energy, or a fraction of this photon absorbed will be transferred, in fact, to the gas and heat the gas through the photoelectric effect, okay? So when we do a kind of balance of energy, a total balance of energy, we see that by direct absorption, the gas gets only a few percent, okay? And then through the photoelectric effect, okay, the gas gets also a few percent of the incoming radiation. So at the end, the emission of photon through line emission is only about a few percent of the total energy that has been absorbed from the radiation field, okay? And most of the energy, when a photon is absorbed by dust, most of the energy is used to heat the dust, and the dust then emits in the far infrared, and this corresponds to more than 90% of the emission. So at this point, so this is just an overview of the problem. At this point, there is two comments to make. The first comment is that none of this emission process produce photon between 5 and 13.6 eV. There is no emission between this range. So oppositely to H2 region, when we had emission of ionizing photons, okay? Here, we don't have emission of photodissociating photons in a PDR, okay? So this is not entirely true. If we take into account cosmic ray excitation, then we will have some UV field created inside the cloud. But if we don't look at cosmic rays for the moment, then we can say that there is no emission of photon capable of dissociating molecules. This is the first point. The second point is that if we only look at this slide, PDR should be boring environment because everything is absorbed by dust, everything is re-emitted by dust, nothing happened. Everything should be controlled by dust. It's even surprising in this with this slide, in fact, to believe that there are several chemical transitions inside a PDR. Why should it be? While most of the photons are completely absorbed by dust. Well, in fact, in PDR, this balance or this way of seeing the problem is wrong, simply because of one fact: all the photons are not as important as one another. There are photons that are much more important for photodissociation than other photons. So even if the dust on average absorb most of the photons between 5 and 13.6 eV, there are some photons that are not absorbed by dust, but these are the photons that are important in PDR, and this is what makes the entire physics of PDR interesting. And this is linked to molecular physics and to the process of photodissociation. So now I have to go to this process. So basically, imagine that you have a molecule and a photon in interaction with this molecule. What will happen is that this photon, there will be a probability for this photon to be absorbed and to bring the molecule into an excited state. Two possibilities here. Either the excited state is a non-bound state, in which case this absorption will lead to photodissociation immediately, okay? Or the other possibility is that this state is a bound state, and in which case what will happen is that then this state will relax in a second step, okay? And there will be three possibilities. Either it relaxes toward a state which is unbound for an electron. This will lead to the photoionization of the species. Or it leads to a state which is unbound for the nuclei. It will lead to the dissociation. Or it leads to a bound state at the end. So it comes back to the ground state of the molecule, okay? And this is just the normal emission, line emission of photons. This is the fluorescence process. So if we think about this two-step process in terms of cross-section, here is what we have. So this is a very nice picture that has been done by Eyes in 2017, where we have on top here the photodissociation process, and on the bottom line, the associated cross-section. So what you can see is that if the molecule is dissociated by direct absorption onto a non-bound state, then the associated cross-section will be spread in energy, because there is not only one single energy that can achieve this transition. In fact, there are many energies that can achieve this transition, okay, with different probabilities, but it will be a spread cross-section. Now, look at the opposite, or the other extreme case. Let's say that the photodissociation occurs through the absorption in a bound state and then a de-excitation towards the continuum here, okay? Then, of course, the cross-section will be very spiked, because the only photon that can participate to this channel is photons are at very precise energy, which correspond to the energy of the transition over there, okay? So in the end, when we are looking at one molecule, and if we want to know the total cross-section of this molecule, what we need to do is sum over all the channel of photodissociation. Maybe this molecule can be dissociated by this process, but also by this process. So we need to sum over all the possible channels for the photodissociation of the molecule and see what kind of cross-section we obtain. And this is a typical result that has been obtained by Eyes. So on this figure, the red curve corresponds to photodissociation cross-section. The green curve corresponds to photoionization cross-section. So you see that on the left side, you have species which are mostly where the photodissociation cross-section is a continuous curve, okay? If you are in this case, then the photodissociation of your molecule will be mostly controlled by the dust absorption of the radiation field, okay? Because dust will absorb most of the photons responsible for dissociating this species. But you see that on the other side, some species are dominated by line processes. So when I said dominated by line processes, they are dominated by this process here. This is the case for CO, and this is the case for H2. You don't see that these are lines, but these are lines, okay? It's just that, yeah, well, you know what I mean. Anyway, okay. So if you have an absorption, in fact, if your photodissociation is dominated by line process, then there can be some effect. In fact, the question that we will have to ask is, who is absorbing the radiation field at this specific frequency? And in fact, this leads to the concept of self-shielding and cross-shielding. So let's say that you have a species here, and you are interested in calculating its chemical abundance. What you will have to do that is, of course, have its photodissociation rate. And if the species is photodissociated in line, you will have to ask the question, what is the intensity of the radiation field at this specific wavelength for photodissociation? And this, then, three cases can happen. Either at this specific frequency, the main absorber is dust, and then you will have a dust shielding, even if it's a line process, no problem. Huh? Maybe dust is absorbing even at the line frequency, okay? Or is dominant even at the line frequency. But there are two other possibilities. Maybe the species, or what counts, in fact, for the absorption at this specific frequency is line absorption by the species itself, by X, okay? Then X, or the photodissociation of X here, will be reduced by all the absorption of the molecules X along this path. This corresponds to the self-shielding. And the final possibility is that you are shielded at this frequency by another molecule Y. This is what is called the cross-shielding. Molecule Y is protecting another molecule from photodissociation because this is the one that dominates the absorption at the correct frequency. So now that we know that, we can finally solve, in fact, or try to apply it to some real case, and we can start with the HH2 transition. So typically, if you want to compute the abundance of any species at any point of your PDR, what you have to do is to solve this equation, which basically, sorry, there is a 0 at the end when we are at equilibrium. This equation equals 0. So basically, it describes the balance between formation and destruction process. So if we consider molecular hydrogen, this equation is simple because we only have to consider two processes. There is two main processes for the chemical evolution of H2, the formation of H2 on dust grains and H2 photodissociation. So regarding the formation of H2 on grains, this is a complicated process which includes physics option and chemistry option sites on dust grain. I won't enter into detail. Most sophisticated model of photodissociation region that treat these processes very carefully. But for the sake of simplicity, I will assume that the formation through this mechanism simply follows this simple equation here, okay, which basically describes, this part describes the number of collisions between a hydrogen atom and a grain. And this rate here is a constant that has been deduced from the observation of H2 in the 1970s, which has this value. So it's just for simplification, but in the models, everything is treated very carefully. Now, if we look at H2 photodissociation, since H2 is dissociated in lines, okay, through line process, then the photodissociation rate simply write like this. What you need to do to compute the destruction of H2 by photodissociation is to sum over all the level of H2 the rate of absorption of photon by this level up to a level U, okay, and then multiply this by the probability for this level U to de-excite towards the continuum, therefore to lead to dissociation. So this is a complete equation to get the photodissociation rate of H2. Okay. So the question is, the only question that we want to answer in a sense is, what is dominating the absorption of the radiation field at the frequency responsible for the absorption, you know, in this level that lead to photodissociation. So in models, actual models, this equation is solved very precisely with a wavelength grid, taking into account the excitation of H2, because you see that this equation depends on the excitation of H2. And here is what is found. So this is a result of the Meudon PDR code obtained by Franck Lepetit in 2006. And this basically shows that for this specific model that you were studying at the time, H2 dissociation is, or the absorption of photon responsible for the dissociation of H2 is dominated by the self-shielding. So this curve here corresponds to the radiation field that you obtain in this range of wavelengths if you only took into account dust absorption. This other curve here corresponds to the radiation field that you obtain if you include absorption by the lines of H2. Okay, so for this example, we see that what dominates the absorption is H2, that H2 is self-shielded. Okay, so this is a very nice result, but the problem with this result is that we don't get a physical insight of why or at which moment it will be true or not, okay? So to do that, we need to adopt or to try to simplify, in fact, the rate of photodissociation. So this has been done by several people, but the most useful for this lecture is the simplification done by Dren and Bertoldi in 1996. The idea is that these people wrote the rate of photodissociation of H2 in a much simplified manner. They basically said that the dissociation of H2 is the dissociation of H2 at the border of the PDR multiplied by two terms, one that accounts for the absorption of the radiation field by dust in this range, which is assumed to be constant, and one that accounts for the H2 self-shielding. What they did was to fit this self-shielding function as a function of the column density of H2, taking into account the line overlap. Unfortunately, this is an approximation, assuming that H2, the excitation of H2, is at local thermal equilibrium at the temperature of the gas. So this was, in fact, slightly corrected by Volcott-Green, okay, this assumption of LTE. And this is the self-shielding function that you obtain as a function of the column density of H2. So now that we have this function, it's very easy to get a physical insight of what is happening in PDRs. What we see here is that the self-shielding of H2 starts to kick in, to be important, when the column density of H2 reach 3×10⁻⁴, more or less, okay? So the question that we could ask is, do we reach in PDR this column density of H2 before or after the dust has absorbed the radiation field? If we reach it before, it means that H2 will be self-protected, shielded, thank you, with this self-shielded. If we reach it after, then it means that the photodissociation of H2 will be controlled by dust absorption, okay? So you can simply take this equation and take the equation for the formation of H2, and you can derive the limit in 1 minute flat. This is why it's so simple. And you will find that the property of your PDR only depend on one single ratio, G0 over NH. You can really prove that very easily. And when G0 over NH is smaller than 3, so this is, be careful, this is 3 cubic centimeter. This is not an high-dimension quantity. This is 3 cubic centimeter. So if it is smaller than 3 cubic centimeter, far smaller than 3 cubic centimeter, then the self-shielding dominates. If it is larger than this value, then we are dominated by dust. And this is what this figure shows. So these are the results of the Meudon PDR code taken from their database of pre-computed model. And what this shows is basically that for low values of G0 over NH, the HH2 transition strongly depend on the value of G0 over NH. When it moves, when it changed by a factor of 10, the transition changes by a factor of 10, okay? This is the effect of self-shielding. But when we reach this red curve here, then we switch from H2 dissociation being due or being controlled by H2 itself to being controlled by dust. And this is why, in fact, the H2 transition is stacked at an AV of about 1, which corresponds to the visual extension at which the dust absorbs the radiation field. Okay. So now that we have seen what happens for what controls the HH2 transition, we can move to other transitions. So I'm not going to describe every single chemical transition that there is in photodissociation region. I'm just going to give you some idea for this transition, for the C plus C CO. What happens here is that the transition from C plus to C is basically controlled by two things in PDR: recombination of C plus on two grains and photoionization of carbon. And the photoionization of carbon is mostly controlled by dust absorption. Dust is absorbing the photons that are photoionizing the carbon. It's not entirely true. There is some contribution from the carbon itself. Okay, the carbon is somehow self-shielding itself a little bit in PDR. But mostly this is it. So this is very easy to extract a criterion for the transition from C plus to C in a sense. However, it's much more complicated for CO. And the reason for CO is that CO is destruction, or CO chemistry is controlled by photodissociation, but there are three effects that can matter, in fact, in the photodissociation of CO. CO can be shielded by dust, CO can be self-shielded, and CO can be shielded by H2. The photodissociation of CO happens in line, and those three processes can, in fact, be important in photodissociation region. It depends on where you are in the PDR, and it depends also on the property of your PDR. So sometimes, in fact, the shielding of CO by these different processes is such that you can even kill, in fact, the transition C plus to C, in fact, and only see a transition C plus to CO. So now that we have seen what are the chemical transition, we can talk about the thermal state of the gas. So we will do as before, look at the heating source and the cooling, or heating rate and cooling rate. So in PDR, there are many different heating rates. There is the photoelectric heating that we will discuss in a minute. There is also the heating by collisional de-excitation of H2, heating by excitation by H2 formation. There are many sources of heating of the gas. But to simplify, I will only consider here photoelectric heating. We can discuss about all this other stuff later. Photoelectric heating is, as you know, the fact that when a photon is absorbed by dust, it can emit a photoelectron, which thermalizes with the gas, therefore heating the gas, right? And in fact, this photoelectric heating is very easy to write its formula. For a dust with a charge Z, and a size A, the photoelectric heating rate simply writes like this, where this part is simply the absorption rate of photon by dust multiplied by Y. Y is the yield. It's the probability that one absorption will emit a photoelectron. Okay? And the right part is simply the distribution of energy of the photoelectron. So you integrate this distribution over the energy. So what we see is that, of course, then when you have this rate for one charge and one size, what you have to do is to integrate over charge and integrate over size to get the total heating rate. But what we see here is that, of course, this heating rate depends on many things. The dust composition, which will play a role everywhere, in Y, in sigma, in amine, in Emax, in, well, every single thing. It depends on the dust charge, on the dust size, and of course, on the radiation field, okay? So it's very complicated to try to get some physical insight on something that depends on so many different stuff, okay? So to simplify, people have come up with very smart approximation of this heating rate, and in particular, Bex and Tillens in 1994. They basically say that the photoelectric heating rate, it's a simplification, writes like this. And this is a very nice simplification because it gives a strong physical insight. What is 10 to the minus 24 times G naught times NH is simply the rate of absorption of energy by the dust, okay? And so what you write in this equation is that the photoelectric heating is the rate of absorption of energy by the dust multiplied by photoelectric efficiency, the efficiency to heat the gas at when you absorb some energy by dust. So this is how Bex and Tillens parameterize this photoelectric heating. And what they showed is that, in fact, this epsilon parameter only depends on one single physical quantity, which is G naught times the square root of T over the density of electron. And this is the value of epsilon as a function of this parameter, okay? So what you can see is that epsilon in PDR, photoelectric effect efficiency, range between less than 1% to a few percent, depending on the physical condition of your PDR. And this figure is very nice. It was done by Wolfire. It shows that the emission, for instance, of C2, C+, in typical PDR never exceed this photoelectric efficiency. Okay, so now if we look at the cooling, I will go quickly here. The cooling is dominated in PDR by collisional excitation, sorry. And I include collisional de-excitation because sometimes this term can be a heating term. This is especially the case for H2. We are going to see that in a minute. But this is the main cooling term in general. Cooling is dominated by collisional excitation. Second term that may influence the cooling is the recombination of electrons on two grades. So I just put it here. It's not per se a dominant cooling term. This term must be seen rather like a reduction of the efficiency of the photoelectric effect. Okay, this is how it is treated usually, but I separated here for the figure you are going to see in the next slide. Okay. There are many other cooling terms in PDRs. I'm not going to describe them. I just will focus on this term. All the other terms we can discuss them afterwards. Okay, but it's to simplify what I'm going to say. So then, once you have the heating term or heating rate and cooling rate, you can compute the temperature of the PDR at every single position. So you can choose the temperature as a function of AV. And this is typically the kind of temperature profile that you will obtain. So this has been obtained using the Meudon PDR code and their database for a density of 10 to the 2 per cubic centimeter. And these different curves correspond to different values of G0, ranging from 1 to 10 to the 6. So what you see in this figure is many, in fact, there are many different effects that play in this temperature profile. But the first thing that we can say is that at small G0 value, when G0 is small enough, then we see that the temperature increases when you increase G0. This is a behavior that is completely different from, let's say, H2 region. In H2 region, we have seen that the heating rate doesn't depend on the intensity of the radiation field. In PDR, this is not the case. At low value of the G0, the heating rate is directly proportional to the intensity of the radiation field. Then what happens is that when you reach some critical value, there is a saturation of the radiation of the heating due to photoelectric effect. And this is shown by this figure. At some point, the heating rate is inversely proportional to G0, but the efficiency of the photoelectric effect is inversely proportional to G0, while the heating is proportional to G0, so there is no dependence anymore. So there is a saturation of the photoelectric effect at some point. But on top of this saturation, we have to add the cooling by the recombination onto grain, which depends on G0, which is larger when G0 increases. And this is why at some point, at some critical value, the temperature at the border of the clad decreases when you increase G0. It's counterintuitive, but this is what happened. Okay. Then another aspect that we can see on this figure, so we have understood the border temperature, is that there seems to be some kind of bump of temperature at some point in the PDR. In fact, this bump in temperature is entirely linked to the HH2 transition. And the reason for that is that, in fact, you have, at this point, a heating due to collisional de-excitation of H2. What happens there? What happens at the HH2 transition is that you have a lot of H2, because H2 is started to be formed, and this H2 sees the UV radiation field. So it absorbs the UV radiation field, okay? And when it absorbs the UV radiation field, it goes to an excited state, and then by fluorescence, it goes back to the ground electronic state. But when it goes back to the ground electronic state, it is in an excited row vibrational level. And this level has some probability to de-excite collisionally. So you see that because of H2 pumping by the radiation field, you channel the energy from the radiation field to row vibrational excited state of H2, and this state can de-excite collisionally, and then it hits the gas. So this is what happened in this part of the PDR, and this is why the temperature increasing. In fact, it is a very important part of the physics of the photodissociation region. So now that we have solved H2, we can move on to the rest of the chemistry. So there I will go very quickly. Basically, we could do, as we did for the HH2 transition, identify the main formation and destruction reaction of every species, and then try to find some sub-networks that will describe the chemistry of different species. So we can do that. And we will find, depending on the position in the PDR and the parameter of the PDR, some families of species which have some kind of pattern in their chemical reaction, okay? But obviously, I'm not going to do that here. What I will say is one message is that in general, there are no rule, okay? We can look at specific families, but in general, in order to solve the chemistry in a PDR, we need to include a lot of processes, microphysical processes. So we need to take into account of all gas phase processes, including photoionization, photodissociation, cosmic ray ionization, and two-body reaction, which include recombination, radiative recombination, dielectronic recombination, and dissociative recombination, but also ion-neutral reaction and neutral-neutral reaction. And we need to include also surface chemistry, which might be important inside the cloud for the formation of several species. So this is one message, is that if we want to model then the entire chemistry of a PDR, the entire chemistry of a PDR is not dominated, but all of these processes can play a role at different points in the PDR. Yeah. Another thing that we need to include inside the models is the so-called warm chemistry, or the chemistry given by warm H2, or the state-to-state chemistry. So in fact, in the two-body reaction that I listed, in the two-body reaction, that were listed here in the chemical network, there are some reactions which are exothermic and other reactions which are endothermic. And in fact, in PDR, a very important aspect of the physics is that you have two ways to overcome the endothermicity or the activation barrier of endoenergetic reaction. Either you do it through thermal collision, okay, so the endothermicity of the endoenergeticity of a reaction is overcome by, let's say, the thermal energy of the gas, okay, in which case your rate write like this. But there is another channel in order to build or to overcome endothermic reaction is through the internal energy of the reactant. So how does it work? The same way as the heating by H2 works. Basically, you have H2, there is a radiation field, H2 can absorb this radiation field and it will lead to the excitation of H2 in low vibrational level. And this leads to a channel of energy from the radiation field to the internal energy of H2. And this internal energy of H2 can be used in order to overcome this endothermicity. So this has been shown, in fact, by many specialists of quantum chemistry, and this is illustrated in this figure here. So basically, each of these figures show the cross-section for the formation of CH+, depending on the energy or the level of H2 as a reactant. And you see that when we increase the energy of the reactant, what happens is that the barrier, the energy at which the reaction happens, shifts to the left of this figure and eventually disappear when the energy of the reactant is larger than the barrier of the reaction. Okay. And this has important impact. And here is an example. So on this figure, I show you the prediction obtained with the Meudon PDR code for a medium with a density of 10 to the 5 and G naught of 10 to the 5. So this corresponds to a hot and dense PDR. And this figure shows typically the evolution of the density or the abundance of CH+ as a function of AV. And what you see is that CH+, which is formed through an endothermic reaction, is basically formed in a region where the temperature decreases and where it is too small, in fact, to activate this reaction. What leads to the formation of species like CH+ and SH+ in this environment is the production of a large amount of vibrationally excited H2. Okay. So how much time do we have left? 2 minutes. Okay. So it's good. It's I only have 20 slides. So so no, just to go quickly, once we have the chemistry, the chemical structure and the thermal structure of a PDR, we can look at typical spectra. So we can come back to this later if you like. Huh? But this is the typical spectra that will be emitted by a PDR. So in this spectra, you will see some continuum here, which correspond to scattered light. Here you will have the pH emission, here the dust emission, some lines which correspond to the vibrational lines of H2 and some other molecules and atoms in this region. Other lines at higher wavelength, which correspond in fact to fine structure lines. So for instance, here's the fine structure line of C1. And well, I think I won't have time, in fact, to talk about some examples, maybe one example, and I will stop there. So from this spectra predicted from a photodissociation region, we can, of course, do a lot of things and make some analysis of observation. And as an example, I took the Orion Nebula, because it was the one I used for the H2 region, and it's a very nice environment, and it's an environment where we have a lot of observational constraints. So basically, over the years, there have been a lot of observation of the photodissociation region in the Orion Nebula, and this is what is shown in this figure. So on each panel, you see the emission of different species in different lines. So here you have the different rotational lines of CO observed by Herschel up to J equal 23 to 22. Here you have the raw vibrational lines of H2, which have been observed by Spitzer, I guess, up to the V equal 2 to 1 transition. Here, the rotational lines of CH+, and here of OH, observe all in the Orion bar. And what is quite impressive, in fact, so the black line corresponds to a model obtained with a Meudon PDR code, and which was shown by Christine Jomelin in 2018. What is quite remarkable is that a single model with a simple geometry, a plane parallel slab of gas, is able by itself to somehow reproduce the entire complexity that we see in the observation. Not only reproduce the chemical structure, but also the excitation structure that we see in the observation. So of course, people would say, oh, well, there is a discrepancy here, but come on, this is a 1D model. There is no discrepancy at this level. Then you can refine your model as much as you want, but it's quite remarkable to have this kind of description. And this is obtained with a typical gas pressure of 3×10⁸ Kelvin per cubic centimeter, adopting a radiation field which is coherent with the radiation field generated by the trapezium cluster. So I will stop here, as there is many examples, but I will stop there and I will go to my conclusion. Thank you.
Maybe we can 5 minutes. Like, but please save technical questions for the Slack or follow-ups for the Slack, okay? You're hungry, or did I discourage you from asking questions? I wanted to see if the students have questions first. Yeah.
Could you just quickly redefine G0?
Yeah.
Thank you.
It's easy. G naught equal G naught. In my definition, oh well, in fact, it's not that easy. But in my definition, in my lecture, when G naught equal 1, it means that my radiation field is the green points there. Okay, this is for G naught equal 1. If G naught equal 10, then you move these green points 10 times above, and this is your input radiation field. Be careful, this is my definition to simplify, but in the literature, it will not be the case. G0 has been defined based on the Habing radiation field, which has this energy density that you have here. When G0 equal 1, then you can take whatever spectrum you want. You need that the integral the flux of the energy flux of your spectrum amount to this quantity, which has been normalized to the Habing field. So there is a difference between my lecture and what you will find in literature.
Anyone else observing?
So you showed that these 1D models that they worked for Orion. And yeah, so if you just look at a local parts of a PDR, like of course like the closer you look, the straighter it looks. But can you think of any like geometries where this wouldn't work?
Yeah. So for instance, in the diffuse gas, no, but these models, of course, when you apply it to very nice geometry like planetary nebula, Orion bar, and so on, when you, as you said, when you look close enough, then you will get close to the geometry that you want. But there are many geometries in which it wouldn't work necessarily. Wait a minute, where am I? So, no, yeah, maybe I should say two things. Okay. So first, when you look at the diffuse gas is basically a gigantic PDR, okay? But it's absolutely not a slab, 1D slab, okay? There are filaments, there are some sheets, it's complicated. And in fact, you need to solve the radiative transfer in 3D generally to have the correct view of the chemistry inside this environment. Then your question was, in which case we are away from this 1D idealized structure. In fact, in some cases, I have shown that the 1D model are doing a good job at explaining observation, but sometimes they are not. And for what I understand, in H2 regions, there is a problem, for instance, with the temperatures that you deduce from different tracers. When you use different tracers to deduce the temperature, when you get sometimes are very strong variation of the temperature, that people to solve that, they always say that it is associated either to some kind of substructure with high densities, okay, which is not accounted by 1D model, or they say that it is due to shock excitation, stuff like that. So
let's close with a question, and then whoever wants, we encourage you to stop the speaker, sit with them.
Yes. In fact, it's a question on Slack. So, but the question is, you're speaking a lot about dust in PDR and not at all in H2 regions.
Yeah.
Why is it?
In fact, I guess I said that at the end of the H2 region part. I said that I have neglected a lot of things in what concerning what I talked about when I talked about H2 region. And one of these was the dust. And indeed, dust can be important in H2 region for several reasons. The most important reason is that it can absorb, in fact, the radiation field. So if we come back to this absorption cross-section, and you see that the dust absorption cross-section is around here, it will seem that it is below the other absorption cross-section, but be careful. This absorption cross-section has to be multiplied by the density of the species. So in reality, it's much lower than that. So dust can absorb the radiation field and basically reduce the Strömgren sphere and stuff like that. And another effect of dust in H2 region is to interact with the different species. Okay, so you have recombination and stuff like that can maybe occur in H2 region. This is what I would say. And a last effect of dust is about the dynamics of the H2 region due to the radiation pressure. The radiation pressure will act on dust, and it will have a lot of impact on the dynamics of H2 region. But I cannot talk about all of this stuff. It's impossible, in fact, 2 hours.
So thank you very much again.